Hello everyone, welcome back to the Techers. My name is Surmeet, and for this video I am going to explain a little bit more about the basics. Um, so for this one we are actually going back to how does a computer actually converts every data that we have, like a complex data, A, B, C, D, colors, everything back to zeros and ones. Because as I've shared earlier as well, and a lot of people might already know, that the computer actually just understands the value of zeros and ones. Now, how does it actually converts the data from the complex data to 0 and 1 and backwards to actually display to us and communicate it with us? I mean, even right now, the current new technology that new application came out is the Chat GPT, and it's a very big artificial intelligence program. And even that is actually just communicating. The computer is actually implementing all that complex data back in zeros and ones. Now, how does it do that? And I'm gonna show you how, like, very like a basic introduction on how it's happening. So as you can see on my screen, I'm sharing it like in a picture-in-picture, so I will be very small and my screen would be a bit bigger. So you can see on my screen, as I've explained to you guys earlier, that the ones and zeros are nothing but voltages. All right, so I've written over here in the graph is plus 5 volts and 0 volts. So it's not necessarily plus 5. Plus 5 is actually just the most common one that is used. It's the most not just used, it's the most common one that most devices actually work on. There are some more devices which are coming are 3.3 volts also. So whatever that voltage, whatever that device actually works on, that voltage would be your 1 and the other would be 0. All right, so wherever in any storage section or anything, so even when you're communicating with the wires, and in the wires when your data is actually getting transmitted, it's so the serial the data is actually getting transmitted. So wherever there would be a voltage getting transmitted inside the wire would be perceived by the computer as 1, and if there's no voltage, that would be perceived by 0. And same as in like newer ones is coming as optical fibers. In optical fibers they're using light, so whenever there's a light detected in the end of the receiver would be considered as 1, and if no light, it's 0. Light they're using because it's common sense. Light is the fastest traveling, like it has the maximum speed, 3 into 10 raised to the power 8 meter per second. So nothing is faster than light. So that is like the fastest communication that can happen with the help of light. That's why that thing happens. So just to understand how the zeros and one is perceived, we need to go a little bit back to the history. So for example, in the earlier times, the computers used to use, I mean, you can see on my screen, this is a example of a punched card. So wherever there is like in punched card, wherever there would be a punched, like there could be holes or there could be like highlighted like this. So on that place it would be perceived as 1. The other places would be, the blank places would be perceived as 0 by the computer. So that's how. And in the earlier times they didn't had the hard drives or any other storage devices, so they would store all their data on the punched cards like this. I mean, I'm not that old, but I just know. I'm just curious. I just know about that. And then yeah, from punched cards the technology went further into magnetic tapes. So if you can see, this example is like a magnetic tapes. I mean, when some people who are video editors, or they would have their new software which would have the something looking like the softwares would have things like this this tape kind of symbol on the softwares. So yeah, that's where it came from. And same magnetic tape logic used to be used in earlier VCR tapes, your cassette tapes for your audios. I mean, yeah, that when I was a kid, we used to have like audio tapes for getting the album songs and stuff. And same thing, floppy drives. So floppy drives, for people don't know, floppy drives used to look like your save icon. So save icon is actually came from floppy drives. Uh, yeah, basically because every data used to be stored in floppy drive. As I said earlier, there was no hard drive, so every data used to be stored in floppy drives, and they had the same thing as magnetic tape. So what does happen on magnetic tape is, so the tapes would be magnetic and they would have small iron or iron particles on that, like very microscopic. You can't actually see on them, you can't touch them, it's very microscopic. Only the read write head or actuator, whatever mechanism, read write mechanism inside your device, they would be able to actually read wherever the magnetic particle is aligned or polarized or something. We don't need to get back too much into the history. This is just to explain why does 0 and 1 come from. So wherever they would be the iron particles, that would be perceived as 1, and any blank spaces as 0, and that would actually convert back into the zeros, and 1 would be converting back into videos, audios, or your other programs or everything. Yeah, so that's how it converted. And then the drawback of those woods, that if there would be a very strong magnet or something, they were very easy to corrupt the data. I mean, when we used to have the audio tapes, we were said do not even touch the magnetic tape parts. I mean, I was a kid, I used to touch it and the data used to be corrupted. All right, so that was a lot of things. Even on the floppy drives, if you touch the magnetic tapes on the, it's not easy to actually get, like, it's still protected, but you can easily actually get access to the magnetic tape and the data would be corrupted. Now even, oh yeah, so even the magnetic tape, same logic is actually started being used in hard drives. So all your hard disk drives started using the same logic. And yeah, so the bigger storage and the actual starting of the modern computers came from which had a hard disk drive, RAM, and all that stuff. Now this actually modified into further because it has a drawback. They started using transistors. I've explained in the earlier videos, transistors came into place. So they used to use, they started using transistors to store the charge. I mean, you can see in this diagram, they have, you don't need to worry about M5 and M6, only M1, M2, M3, M4. They would actually keep the charge in the loop. So wherever there is a voltage, they would keep the charge in the loop to actually store the data. Yes, you can use capacitors to store the data, but that would be temporary and it would actually make your circuits like really, really big, because transistors, these MOSFETs, these new technology, they can be scaled to a microscopic level, nanometers. Your capacitors will never be nanometers. So yes, they started actually doing, and this is more robust to actually store the data. And this is actually, this 4 transistors back to back are actually storing just 1 bit, only 1, 0 or 1. And actually, if you compare M1 and M2, and similarly M3 and M4, is actually CMOS, which is complementary MOSFET transistors. I will explain more later how does a complementary MOS actually works. And your entire logic circuits inside your everything actually starts from these complementary MOS circuits. So everything in your has like you can scale it down like to the microscopic level. It's just this actually making every other device, everything. So from your RAM, from your processor, from the mobile, everything in your logical ICs, everything is actually coming from MOSFETs. So yeah, and let's get to how to actually convert a data. So let me give you an example. Every bit or every data has, like, for example, an A. Capital A would be actually given an ASCII code. So ASCII has like a conversion codes. So would have an ASCII code of 65. So that's a capital A. And for computer to, that's actually used for computer to perceive. So 65 would be capital A. Now 65 would be converted then into binary. So how do you convert it into binary? For example, I'm not taking an example of 65, I'm taking an example of 16. How does a 16 is actually represented? 65 will be a very big number. That's why I'm like converting only 16. So how do you do it? So you start dividing it by 2 because binary is in the base 2. There are other numbering system used in computers would be binary, octal, hexadecimal, or there are other base 32, base 64. There are some companies that use, like BMW has their own encoding which is in base 32 or base 64. Yeah. So that's how that happens. So if you want to do binary, it's a base 2. So you start dividing it by 2. So when you divide 16 by 2, you get a quotient of 8 and the remainder is 0. And you divide the quotient again by 2 until you have nothing left further until 1. You keep on repeating. And when you have to write the number, it's in reverse. So you start from the last quotient or the remainder and track it back to the top as shown in the arrow. So your 16 in binary would be represented as 1 and 4 times 0. All right. So as I said, there are more numbering systems like octals. So if you want to do for octal, that is a base 8. And similarly, you divide it by 8. So your 16 would be represented as 20 in octal, 20 in octal. All right. So because 8 to 16 and 0. And similarly, if you want to go to hexadecimal, you divide it by 16. So hexadecimal, it would be 1 and 0. So 10 would be hexadecimal for 16. Now here's the confusion. If you want to convert 10 to 15, your remainder would always be just still 10 to 15, but then there would be confusion. Is that 10 as a 10 or 10 as in 16? So to avoid that confusion, from the numbers 10 to 15, they're actually represented as A to F. All right. So that's how it actually starts doing it. I mean, if I have to show you, you can see on my Android programming screen, you can see over here, I have a background color which is actually has EDE089. That is all hexadecimal values. So that's how it's actually used. That's where your hexadecimal will be used. All right, that's a little bit advanced. We're not going there. It's already 12 minutes into the video and I want to keep it short. I don't want to bore you guys. All right, so that's all hexadecimal value happens. All right, more to that is we will come back to, I have a complete chart. All right, and here is something that if you want to convert back from binary to actually your decimal values which we perceive, so our normal numbers 0, 1, 2, 3, 8, 16, 24, whatever we write, that is base 10, which we perceive, which we normally perceive as a decimal value. If you want to convert back from binary to decimal, so for example, this is an 8-bit line because it's just I'm using 8-bit line. So you go from, so your rightmost bit in this would be your least significant bit, which would start from the indexing of 0, and you increase from right to left, you increase. So the right one would be the 0th bit, so it would have as index 0. You give it to power from 2 raised to the power 0, and the left one would be 2 raised to the power 1, and you can see it's actually increasing 2 raised to power 1, 2 raised to power 2 to 2 raised to power 7 all the way till the 8th bit. And if we solve those, it becomes the values which is given under. So 2 raised to power 0 is 1, then 2 raised to power 1 is 2, and so on until 128. Now what happens is, if you have whatever number you have in binary, for example, we made 16, which was 1 and 4 zeros, you will start filling up from, so 140, it would have 16, and then it was 0, 0, 0, 0. So wherever the 1 is, you would take that number. So 1 was at 16th place. You will take that 16 and then plus every other one's location. But in this case, it was just 0, so that would become 1. Another example, if it was at the 16th place, if it was 1, and at the 1 place, it was also 1. So that would become 16 plus 1 as 17. And same as 16, and then it would be at a place of 4 and 1. It will become 16 plus 4 plus 1, that is 21. That's how your number conversion back would happen. Okay, and you can use the same logic for octal numbers or hexadecimal numbers, you will just use 8 to the power 0 for octal, 8 to the power 1, and for hexadecimal it would be 16 to the power whatever it is, and whatever your number would be, you will multiply that. So for example, it was, let's say 331 in hexadecimal, so you will have 16 to the power 1 multiplied by 3 plus 16 to the power 0 multiplied by 1 multiplied by 1, and you add both numbers, that would be your answer. And yeah, so most of the times we just use hexadecimal and binary. That's what I've mostly used. I haven't used octal as much or any other bases as much as binary and hexadecimal, or even decimal numbers in programming. So here's and then there's another form. So mostly we use this grouping of 4 bits, which is 8421, just for easier programming. We actually mostly use in microcontrollers and most of the places as 8421. As I showed you earlier in my Android programming, the color codes, it had ED and all that stuff. They're all just grouped into 4 bits. It would be an 8-bit data. The complete data would be 8-bit, but it would be separated also in 4 bits. It just makes it much easier for programmers to understand and write the code, because 4 bits is much easier. Actually, just it's less data for us to actually keep in mind and do the programming. Now 8421 coding is also known as BCD coding. Don't need to remember the full form, binary coded decimal. And in that one, so here's a chart how actually all the numbering starts. As I said, in 8421, your 0000 would be represented as 0. So 0001 would be, it's only in one place and all the others are 0, so 1. If at 2 place 2, so you can see in 3, so 2 plus 1, that is 3, so it's at 2 place 2 plus 1 is 3. Same 4, so 6 would be, so at 4 place at number 4 there's 1, and then number 2 at 1. So both 4 plus 2 would be 6. Similarly 7 would be 4 plus 2 plus 1, that is 7. And BCD only happens till 0 to 9, that is just BCD. If we include 10 to 15, yes, your 4 bits can actually make your number from 0 to 15. But if you actually go from 10 to 15, that is hexadecimal. It's not BCD anymore. BCD is only until 0 to 9. All right, so yeah, so that's the thing. And as I said before, hexadecimals have the value as 10 as capital A, 11 as capital B, 12 as capital C, and 15 as capital F. All right, so that is a little bit of how the data conversion actually happens into the binary. And I will go back from the next video. It will be more like how all the colors can happen, so how the red, green, blue, how did I make the color coding, and also how to make the logic circuits. So everything I showed is based on transistor logics. How to actually make the logic circuits to transfer this 0 and 1, perceive the one type of data and convert into other, which would be more useful for our LCD programming in the microcontrollers, like 7-segment display programming, or even the LED matrix programming, or LED cubes, based on like how to actually make those logic circuits is the basis of every IC designs. So okay, so we'll go back to, it's already 18-19 minutes into the video, and props to those guys who are actually still watching. I know these topics are not as interesting, but to whoever finds it interesting, props to you, and I'm here to help. Let me know if I can help you guys in any other way. Just keep your comments. I can give you topics, give your comments, and I will try to make videos on that. So it's a simpler introduction, simpler explanation to whatever doubts you have. All right, so thank you guys, see you next time. All right, bye.